Where's the microphone?
Okay, so first, we are now being recorded. Okay. Julia was a little premature, but now we are. Sorry, microphone's back a little bit because I'm going to use this size. All right.
Hi, Jack.
All right. Today, I wanted to walk you guys through the first part of your lab. This is your first physics lab. This is your first LabQuest lab. So I wanted to go through some procedures, but also talk about you analyzing some graphs, because if you've never seen them before, it's hard to sometimes, determine what's going on. Okay. First things first. This is the motion detector. Okay. Obviously, if you're watching at home, you can't see it, but that's all right. So here's the motion detector. Okay. It is green. It does kind of look like a walkie-talkie. It doesn't have like a little Morse code button on the front of it. So I got the impression that some of you may have used this last year.
I was just walking the walls with it.
We'll do that lab.
It's so much fun.
All right. So as far as the motion detector goes, for those of you that did use it, maybe this is a refresher. For those of you that didn't use it, here's how it works. Okay. When the motion detector is plugged in, you'll hear that it makes a clicking sound. Okay. It may click fast, it may click slow, depending on what the settings are. What it's doing is it is creating a sound wave. That sound wave is going out into the room. It bounces off of things, and then it comes back to the motion detector. The motion detector basically knows how fast the speed of sound is, so it records the amount of time that it takes to get from that object then back to it, or then back to the motion detector. And based off of that calculation, it can now tell where the object is, what it's doing now, is it changing what it's doing, and then when all of these things are occurring. Those 4 questions that we wanted answered as far as mechanics are concerned.
Okay. We could like run down the hallway and then the recorders.
On page one of your lab, about 3/4 of the way down the page, there is this section called coordinate system. We introduced the idea of a coordinate system back on Monday. We also called it a frame of reference. And we said, Josh, we kind of referenced this before. It's basically just to make sure everybody's on the same page, okay, when we're making our measurements. Today, you are not making any measurements. This is making measurements. Okay?
Thank you.
This is the thing doing the measuring, which means it has to set up a coordinate system.
Peoples.
Pause for a second.
How's this in the middle of class or anything? What is
Things still go.
I know. What is
I need his ID.
You want me to stop recording for this or something?
It all into place.
Is there?
I'll be right back.
Is there?
Begin scanning the halls a lot.
No, I want to do this. I want to do class. All right. So, because the motion detector is making the measurements, it sets up a coordinate system. We said a coordinate system has to include a reference point, then a directional system. Just like in the picture, the motion detector calls itself the reference point. It measures everything relative to it. So 0 is defined as right where the motion detector is. Then it calls everything in front of it the positive direction, and it calls everything behind it the negative direction.
We get everything.
No. So Julia, if we're measuring, remember I told you the motion detector could tell you where, what is it doing now, what is it doing in the future, right? The where is the position. Will you ever get negative position values using this motion detector? No, because everything is in front of the motion detector that it measures. Okay? Now, as we discussed earlier, does that mean you'll never get any negative values? No, because velocity can be negative. You can be traveling in the negative direction, but still be on the positive side of the reference point. What would that look like? How would it measure a negative velocity? Coming towards it would be a negative velocity. Going away from it would be a positive velocity. Because that's traveling, if it calls everything in front of it positive, I saw some funny looks. So, okay. If it calls everything in front of it positive, right? If it's traveling in the positive direction, do you want to draw a picture? Let me do this, hold on.
Wait, but if it
do this. Okay, here.
If it's like on the side, not in front of it.
So,
here's
hold on. Hold on 1 second. To answer your question, the motion detector really only works in one dimension. So it's only going to measure things that are basically directly in front of it, if they're moving directly in front of it. If it's moving side to side in front of it, it really won't pick it up. Okay?
So,
Why don't you draw it up here in relation to this picture that I got for you?
no, I don't.
Go for it.
Okay, so here's a little motion detector thingy,
Okay.
and going this way. Okay, here is this. Okay. So anything over here, this is positive, and then anything over here, this is negative. Okay.
That would be negative position, positive
Negative
position.
So if it goes this way, the position, it's gonna be negative.
No.
Because it's coming towards
Position. The position is still positive because it's still on the.
direction. Sorry.
No. Make sure we get our term straight. Position is where is it now,
So
right?
It's
It's still positive position, but the velocity tells you what is it doing
going
now.
towards the negative.
It's going towards the negative side.
So if this little guy, this is fine. Okay.
Okay.
It's coming this way.
Yes.
The position is gonna be positive.
Yes.
But then the direction is negative because it's coming towards it.
This is just like the second gecko picture that we looked at, right?
But inside the gecko,
Instead of a gecko, it's a flying mustache, apparently.
No, it's
this is a bird. Guys.
Oh, a bird!
looks like facial hair.
No, but mustache has ace. But why?
I remember that one.
It has, I remember.
Yeah.
Why?
We'll work it out.
Oh,
All right. Are we good with the motion detector, at least for now? Hallie might not be good right now. Okay, next thing I'm going to do for you.
So yeah, if you run away from it, you're like,
Yeah.
You invest in some tissues.
So, maybe
what if you like,
maybe some generous students could bring some tissues in.
Extra credit.
Without being prompted by extra credit.
Wait, why would I be
would it mess up the motion detector if I like talk to it for the sound?
Maybe a
waves?
little bit, but it's looking for a
All
right.
Is it really high?
No, it's really not, but.
Oh,
All right.
it's like,
Let's discuss. Okay. Up on the screen right now, that is a picture of what the LabQuest looks like. It's not the actual LabQuest. I have a program on the computer called the LabQuest emulator, which is what it said up top. So it basically shows you what the LabQuest is showing you. Okay? This is what the LabQuest would look like. All I've done is I plugged the motion detector into the side of the LabQuest, okay? And now, if you're sitting close or if you are quiet, you can hear, you may be able to hear it on the recording, that the motion detector is clicking. So, what it's doing right now, all it's doing right now is it's just checking. It's just measuring position, but it's not recording anything. All it's doing is where the thing is right now. So, if you look over here, right, the big pendulum bob, oh, I should do this. So if you're watching this at home, you might not see this part because this doesn't show up so hot. I think it just looks like a big black. I think it just looks like a big black box. Okay, but this is my webcam. Okay, Kartik's there. So, Kartik, I hope you don't have any problem being on the internet. So yeah. So if you get here, here's the pendulum bob. Here's the LabQuest, or here's the motion detector that's hooked up to the LabQuest. So all it's doing is it's sending out sound waves, they're bouncing off the pendulum bob, it's coming back, and it's measuring how far away the pendulum bob is. And if we go back to the LabQuest, you'll notice that it's pretty consistent with a position, because what's the pendulum bob doing right now? Or not doing? It's not doing anything. If I slowly start that pendulum bob moving, okay, just like that, if I go and look at my LabQuest, you see that those position values keep changing, right? They keep getting smaller, they keep getting bigger, they keep getting smaller, they keep getting bigger. Right now, all it's doing is it's just measuring, okay? It's not recording anything. Josh, go ahead.
How come when it was holding still, like the measurements was switching?
There probably was a little bit of motion. if you look, Josh, we're talking like the thousandths of a meter, right? So it's moving it might be moving 1 millimeter back and forth. Or it may be in between a distance of a millimeter, and the lab quest is like, okay, is it this far? Is it this far? You know, so that's just like any kind of automatic measurement, like on the electronic balance. Sometimes we don't always get a real steady reading because of the limitations of the machine and stuff like that. All right, are we good so far? Okay, here's what we're going to do next. On your lab, if you flip it over to page 2, okay, data collection equipment setup, I've already done that part. We are going to work through station 1, oscillating pendulum, together. Okay. So the first thing it says, place the motion detector near the pendulum, right? Motion detector, blah, blah, blah. It's set up just like I was showing you before. Okay, there's the picture. First thing it says, sketch your prediction of a position versus time graph of the pendulum bob swinging back and forth on the graph provided below. Notice I got rid of and velocity versus time graph. So it just says sketch a prediction of the position versus time graph. So first, couple of things. 1, okay, talk amongst yourselves, come up with, okay, what do I think this graph is going to look like for position versus time? 2, it's a prediction. It can't be wrong. Okay, well, it can be the incorrect prediction, but I can't mark it wrong on a lab, okay? So just write it down, sketch it for me, okay? And then later on, when you find out what the graph actually looks like, don't go back and change it, all right? Just leave what you had originally there. It's a hypothesis, okay? If you would like, there are colored pencils up here, okay? If you want to use some colored pencils to whatever distinguish, you may do so, okay?
Position the pendulum swinging back and forth.
Yes, yes. So the way that it's set up, just like this, okay? Don't worry about the little up and down motion. It's moving back and forth in front of the motion detector, basically just like this, okay? Does that make sense?
Yeah.
It's lined up so that the motion detector will pick up the motion in that one dimension. All right, discuss, predict, go.
So it's not actually like waver. It's gonna be like it used to go up and down, and then as it goes on,
I'm pretty sure it's really like that sign.
right, it over.
It's like,
Yeah.
it goes over and then under.
Yeah, that'd be right. I assume it wavers.
Wait, is it, if it's just still, is that 0 or is it kind of like?
Okay, so under the time is that negative is like under the time and above it
Well,
positive.
no, it never goes behind it, so it can't be this.
Prediction. It's a prediction, right? I want you guys to discuss these.
Or would it be like,
Well, or no,
do you
it never
think
really goes behind it.
wait, do you think it'd be wavering up and down or like side or side?
Yeah.
The graph will be like steeper wave.
I'll tell you how it goes far, right? So the reason people want that is because
Oh yeah.
pendulum bobs in front
Right.
of the motion detector, which is the line.
Nice
Yeah,
prediction.
you can't have
So
that.
as it goes on though, it slows down, so it would be smaller waves though.
Right, and start off big and then somehow physics.
Physics.
Volleyball.
Don't hit him.
All right, here's where we're going next. Lab Quest emulator. Okay. Still clicking. Not that we're going to do this now. Okay, I'm going to zoom in a little bit so you can see things a little better. Hopefully this works because I've never zoomed in while I was recording before, but hopefully it does. So. Okay, on the Lab Quest emulator. Over on.
It's not going to that computer, so I don't think it's going.
Say again.
And then go to the computer and zoom in and then.
No, I wanted to zoom in on this.
Oh, sorry.
So you can see it a little closer.
I mean, the people are talking about
It only catches the computer screen.
Yeah. Oh, okay, that's fine. Yeah. So yeah. Thank you. Thank you. All right. Over on the right-hand side over here, these gray boxes, we can change the parameters that we collect data. Right now, it's set. When I tell it to record data, it is set to take 20 samples every second for a total of 5 seconds. Okay? It's a lot of samples, right? But it has the ability to do that. And actually, 20 samples per second is actually a pretty slow sample rate for the lab quest. It can get as high, I think, as 100 samples a second, if I remember correctly. Okay? But anyway, we can change that. We're not going to today, but that's all right. Now, to start data collection, there's two things that we can do. On the touch screen, there's this green button. This is on the touch screen. So you touch it, you're good. Sorry. The lab quest is a touch screen on it. It's got a little stylus on it. So you touch it. So this green button here will start data collection, or this button here, which is actually on the face, is an actual button, will start data collection. Okay? So here's what I'm going to do. Okay? Here's what I'm going to do. I would like. I do need a little bit of help for this. Kartik, you're closest. It's pretty challenging, Kartik. I think you can handle it. So Kartik, what I want you to do is I want you to pull the pendulum bob back just like maybe like an inch or two, right? Yeah, too far. A little closer. There we go. Okay. All right. I'm going to hit the play button to start data collection. You're going to hear first the motion detector stop clicking. Then it's going to start clicking faster.
Okay.
When you hear it start clicking faster, count 1001 in your head, then let it go. Okay, so it's going to stop first, then it's going to start clicking faster. When you hear it start clicking faster, 1001, then just let it go. We'll let it go until it stops clicking. Okay? All right. Are you ready?
Yeah.
Here we go. Okay. All right. There is our first set of data collection. Okay. Now you'll notice one thing that I actually changed in my setting from before. A lot of times, what will happen here? I'll change it back real quick. A lot of times, what will happen? Hold on. It is really cool. Oh, on the computer. Okay. A lot of times, isn't this like convenient so you can actually see what I'm talking about? The modern technology.
Mr. B wouldn't be able to do this.
Maybe not. So, although he may have a child that developed this technology to use. All right. You'll notice a lot of times when you do data collection runs, the LabQuest will automatically scale your y-axis to show you the biggest picture possible. But sometimes that's not what we want. Okay? If you notice on the velocity graph, on the y-axis, the minimum value is negative 0.4, and the maximum value is positive 0.4. Okay? But, well, here, Hallie, this scale shows us the whole velocity graph. Okay? But on the position graph, you'll notice that the minimum value is 0.25, but the maximum value is 0.45. So you don't actually see the x-axis in that picture. Does that make sense? Okay. So here's what I'm going to do. I'm going to go to Graph, and I'm going to go to Graph Options. Okay. And here, I'm looking at the position graph. That's the one that's checked off over here. Okay. I don't expect you guys to be able to do this right away by yourselves. I'm just showing you what I'm doing. Okay. Over here, it has a top value and it has a bottom value. So I'm going to highlight this section, okay, and then this little keyboard shows up on the LabQuest. And I'm going to make this negative 0.2. Okay? And now I go back to my graph, and you can now see the x-axis on the position graph and the x-axis on the velocity graph. Does that make sense? All right. On page 3 of your graph, on page 3 of your lab, the first two questions say, sketch the position versus time and the velocity versus time graphs of the pendulum bob swinging back and forth on the graph provided below. Go ahead and do that now. Go.
Not bad.
So why is the velocity bigger higher ways?
That more has to do with the scale that I set on my x and y axis. Okay. Because that's just showing you. Remember before we changed the y-axis, the red graph, which is just called as the glue graph, right?
Okay.
That has more to do with what you're looking at or what the scale on your y-axis. Okay.
He's a little codon. Aw.
Their dog from out of school.
What kind of dog is it?
Maybe it's like a slab.
Why should be like
Minor district.
yeah, I understand like congratulations, you see the dog. Like why should be like
It's like a plan that.
no, it's like a why is a giant like a shih tzu chasing a squirrel?
All right. Did we get our graph sketched? Apparently, Flavie didn't. Sorry. Oh, there it is. My bad. My bad. All right. Let's start working on these questions. Okay. So the first question on your lab says. Let me do this here just so people at home know what I'm talking about. So the first question on your lab underneath the graph says, what was the pendulum bob doing when data collection began? How can you tell looking at the time versus position graph? How can you tell from looking at time versus velocity graph? So if we go back to our graphs, okay? First, what was the pendulum bob doing when data collection began?
Well, it was still for a little bit.
It was still for a little bit, right? So if we take a look at these two graphs, right? If we look at the position graph, and just so we can highlight some things, okay? Basically, I'm looking at this section right through there, okay? What do we see about the position graph at the very, very beginning? It's not changing, right? The y value is consistent. What are we measuring on the y-axis of this graph? Y-axis. Position, right? If the position is staying constant, what does that mean about the motion? It's not going anywhere, right? It's in the same spot. Second, if we look at the velocity graph, what do you see about the velocity graph at the beginning? It's constant. But where is it constant at? On the x-axis, which means, Kartik, the y value for that graph is what during that time? It's 0, and what's on the y-axis of this graph? Velocity. So if it has a 0 velocity, what does that mean? It's not moving. Answer those questions right underneath your graphs.
Well, the first question is, why was it pendulum bob, or what was it doing?
Hold on with that, Hallie.
So you just say,
It was still.
it was still.
How can you tell by
Yeah,
looking
that's not being hot. Oh, maybe that doesn't make us what
It was still until.
It was still at first.
And then it began to.
It was not shown.
So that's the direction. Not direction, the direction.
By a flat
Line portion
of the graph
of the graph.
It stays constant on the y-axis. Right.
at the
Oh.
beginning.
The first one, yeah. The y value is constant, which means that means the position is constant.
It's flat
It's not going anywhere.
at
And
whatever.
then for the second one, you see, right?
Yeah.
The position.
It's on the x-axis. That means the y value is 0, and the y value is the velocity on the bottom graph.
how far?
Go forward.
You can tell right now.
0.45 meters.
Right yet. All right. Are we good with those questions? Okay. Let's start doing the analysis part. The next question. The next question says. The next question says, you guys can't see it on the screen. It says, how far away from the motion detector did the pendulum bob start? So if we go back, if we go here, okay, if I touch the either of the graphs, you'll see that these little lines, this little dot show up. Okay. Anybody have a TI-83 or a TI-84 calculator? You ever use the trace function on it?
Yes.
Okay. That's basically what this is. Over here on the right-hand side, you'll notice there are 3 boxes. One says time, one says velocity, one says position. When I touch the graph in this spot right here, it gives me the value of the position graph at that point, the value of the velocity graph at that point, and what time was occurring. Time is on the x-axis. Time is the x-axis for both of these graphs. Okay?
Position you part of velocity?
more of a general term. Okay? Position is telling you where, velocity is telling you what it's doing. Okay? All right. With that being said, zoom here, okay? Is this where I put my thing now? Is that the beginning of the graph? Actually, no. Because look, what's the time? 0.10, right? On the face of the lab quest, it has these buttons here. I can go one dot at a time by pressing this button, or I can go one dot at a time backwards by pressing this button.
You could control the lab class from there.
I can actually control my virtual lab quest or my lab quest emulator, but I'm going to show you guys how to do it. So you would actually be pressing the buttons on the lab quest. But I press the buttons all the way until my time read 0.0 seconds. Okay? What was the position at 0.0 seconds? 0.427 meters. So how far away was the pendulum bob when data collection began? 427 meters, right? Technically, what should we label it if we're labeling it as position?
What is meters per second? What
side of the reference point is it on? So we should label it as positive 0.427.
How can the velocity be 0.001?
Kelly, we're talking about limitations of the machine, right? 0.001 meters per second is pretty darn close to what?
Yeah.
Pretty close to 0. Right? So, it's getting some fluctuations in some things. Maybe Kartik wasn't exactly holding it 100% still, whatever.
Sorry.
Or like we talked about, it may just be like in between, like 0 and something else, and it's just kind of rounding or whatever. Okay. All right. Next question says, what was the closest that the pendulum bob ever came to the motion detector? So if I pull my LabQuest emulator back up, oh, not that one, this one, okay. If we look at the motion, or if we look at the position graph, right, it starts off constant, but then what happens to it? Well, it does waver.
It comes to it.
These position values get closer, right? So I'm going to point right there, okay? How do I know that's the closest? Well, I don't exactly just yet, okay? But I have these position values, right? So I'm going to use my buttons to find out what's the actual lowest position value, right? And it looks like that one is the closest it ever got. So, what was the closest the pendulum bob ever came to the motion detector? Oh. Sorry, buddy. Positive 0.258 meters. Okay. What time did this occur? It occurred at 2 seconds. Okay. Those are the next two questions. The next question says, what was the velocity at that point in time? What am I reading here? That is a negative 0.01, which, Hallie, is pretty darn close to what?
0.
Okay. When the pendulum bob comes as close as it's ever going to come, what has to happen at that point in time?
It has to be close to 0.
Well, before it turns around, Kartik, what does it have to do? It has to stop first, okay? So, if I look at the closest points, right, of that pendulum bob, okay, there, what value am I getting velocity-wise? Pretty close to what? 0. Now, remember, we set up our lab quest to take data 20 samples per second, or every 500ths of a second. It's possible we may not have gotten the closest point because it just may have happened in between clicks. Okay? So we do our best and we get the closest that we can. Bitter.
But when you throw something up in the air, does it actually stop momentarily before coming back down?
But
to get more accurate data, we should set the.
we could set up the lab quest to take more samples per second. That would give us more options. Although, Flippy, what that does, though, is if you're trying to find the smallest point, it makes it tough because you have to go through way more points. So, it's a trade-off. All right. Now, let's make some connections. Okay. Next question. Okay. Says, what happens to the velocity graph when the bob passes through the closest point? We've already established that the velocity graph should be really, really close to what? When it should be really, really close to 0. Okay? If you take a look at the next part of our graph, right? Here, from this point to this point, okay? If we look at the position graph, what has happened to the position of that pendulum during the section that I just highlighted?
As far as it can go.
It's gone as far as it can go up, right? So if I go here and say this is the farthest away it ever got, okay? Actually, I'm going to go a little bit further. 0.427, 0.427, 0.423, right? 0.427, so there, okay? If I look at the velocity graph at that point, what's it pretty close to? X-intercept, which means the velocity graph has hit what? 0. Because when it reaches its farthest point, what does it have to do on the other end? It's got to stop there too, right? The next time it swings back close to the motion detector, right? Where's the velocity graph close to? Pretty close to 0, right? The next time it goes farthest away, pretty close to what? 0. Okay? Those have to be zeros at those end points. It has to stop. It gets close to 0. Technically, when it passes through the closest point, it has to be 0. We just may not have measured it in our lab. Okay? All right. Here's where things get a little trickier. Okay? I'm going to highlight this section, and this isn't exactly on your graph, or this isn't on your lab, but it'll help us for the next part. Okay? Christina, you already told us that during this section, what has happened to the pendulum bob during that section? So it started as close as it was going to get, right? And now it's as far as it's going to get. Okay? So, I can't remember kind of said this before. Which way is it moving relative to the motion detector? Towards it or away from it? So moving away from it. Which direction does the motion detector call that? It calls that the positive direction. We said anything in front is positive, anything behind is negative. If we look at the velocity graph here, where are all these velocity values? Above the x-axis or below the x-axis? They're all positive velocity values. However, what has happened to the velocity during this trip? First it got fast, then it got slow. You ever been on ocean motion before at Cedar Point?
With my little sister.
Okay. Where are you going the fastest on ocean motion? When you're through the middle,
Yeah.
right?
I'm trying to go around the back seats. Hers is the best. She won't go there.
You ever been on?
Oh, the boat?
Yeah, both. Yeah.
Oh. It's like right in the front.
So, there. If you've never been on it before,
It's a boat that goes like this.
It's like
It's a
really
big pirate
fun.
ship that's like.
Oh,
it goes back-
intentional.
Yeah.
Did they take that down for the?
No, they moved it.
My favorite one.
Yeah, it's like right up in the front where
My
Demon Job
favorite
used to be.
one's Skyhawk.
So,
It's always a demon.
yes.
So when it's on what axis, it's at like either it's on.
Have you been on?
It's on one side.
What else
Yeah,
outside?
because the velocity is 0.
That's
Oh, no, that's like, there's one called Skyhawk, kind of like it,
Yeah.
but it's for bigger.
I wrote Skyhawk last year when I went to Cedar Point with physics kids, and I really thought I was gonna hate it. I really thought I was gonna hate it.
I
like,
love
a lot.
that one.
And it was actually way
What
cooler
ride?
than Skyhawk.
Oh, that's
Wasn't it really fun?
Wait, we go to see it.
Little ones.
I like
No,
it.
that's Max Air, I think. So,
Yeah,
but, like,
Max there's like the
Skyhawk is like way in the back, like by the Maverick. It's way back.
Oh.
Yeah, I really thought I was gonna hate it, but a couple
It
people
feels like
made me
you
go
fall
out. They're
out.
like, "Come on, come with me, come with us." So I was like, "Okay." And I went on it, and I was like, "This is way cooler than I thought it was gonna be." So, this is way cooler than I thought it was gonna be.
Wait,
So,
we go to see it.
No, I can't have like
It goes really high.
like space.
You know,
It's
don't
so
trip every time.
So-
No way.
the end of the unit card if we go.
Still,
All right.
We should go see it.
Let's
All
study
you
physics.
all you have to do is take physics. That's what we can do.
Really?
It is physics.
Why?
What's physics
You
actually
can
about?
pretend it's
What year is that?
senior year usually, but it could be sooner than that.
Is that eighth physics?
But
No,
by the
that's
time we
regular
get
physics.
to budget,
Not conceptual.
What's concept? Do you go for 8?
Yes.
Yay!
Alright, so now, okay, let's do this part. Christina, see this section of the graph that I just highlighted here?
Yeah, it's going back.
It's going back towards the motion detector. Okay, now here's where things get a little trickier. Okay? If it's going back towards the motion detector, which direction is it traveling? It's traveling in the negative direction. It still has positive position values, but it's negative velocity.
I just put on the thing saying it's going towards the north.
Yes. Yeah.
Right? It's because
That's Missy, that's a great way to say it.
So,
Wait, what did you say?
Now, here, let me do this part, okay? Alright. Here, this section, from this point here to this point here on the velocity graph. Okay? What's happening to the velocity during that section right there? It's going negative, but what's happening to it's speeding up. Okay? Because good. Let's look at the values. What's happening to the y values during that time? No.
Wait, sorry.
They're getting farther away from what, Hallie? Zero. And for velocity, that means you're getting faster. It just means you're getting faster going in which direction? Towards the motion detector. Okay? If I look at this point here, okay, 0.309 is the velocity at this point. And then if I look at this point, okay, negative 0.315.
Oh, because that means that you're going at a farther speed in the whatever
How,
second that is.
how fast am I going at those 2 points?
You're going what?
You're going really
Is
fast.
this fast, relatively speaking?
Yes.
Yes. Is this fast, relatively speaking? Yes. I'm going the same speed, but a different direction.
Yes.
Okay.
So the velocity is different.
So the velocity is different, but that doesn't mean I'm not going fast.
But it just means faster. That direction.
Right. Yes, you go ahead.
So for this case, like the farther you get away from the x-axis, the faster you're going.
Yes. On a velocity graph, the farther we are from the x-axis, the faster we're going.
I was like always good.
On velocity graphs, yes. Okay. Carter, go ahead.
Sorry, it's a little off topic.
No.
When it changes directions,
Yep.
is there a little tiny flat part at the
No,
very bottom?
because Kartik, that's a really good question, Kartik. No, because I'm not getting it here. But anyway, as close as we get. Kartik, it is stationary for such a short period of time that it doesn't show up as a flat part. As you can see here, it only hits the x-axis in one spot. So there's only one instant in time when it's actually at rest. Okay? So yeah, it does hit rest, but it's for such a short period of time, it's basically one spot here. Okay?
Wait, why is it right?
Because it's as close as I can get it, Sadie, but what's the y value of this graph during that time? What is the y value of the blue graph right there?
Oh, it's 0.
0. And what's on the y-axis of the blue graph? The velocity.
Oh, yeah.
X-axis. Alright, go ahead.
At the top of those individual peaks, that's sort of like S.
So, if you look, that's actually the next question, okay? If I look here, right, I'm going to go down here, and I'm going to make my velocity as big of a negative number as I can. So it's right there, okay? That's the fastest it's ever going towards the motion detector, right? Christina, if I look up at the top here, come on, move back there. If I look on my position graph, where am I relative to the farthest point and the closest point? About the middle, right? So yeah, Kevin, like you said,
That's when it's flat right there.
that's when it's basically where it is right now. When it's passing through the middle, that's the fastest you're ever going. Just like on ocean motion, if you've been on ocean motion before. You're never going any faster than you're going through the middle. You speed up on the way towards the middle, you slow down on the way back from the middle, or away from the middle. Okay? So, The next two questions says, what was the time when the pendulum bob was directly in the middle of its path? 1.60 seconds. What was the velocity at that point? Negative 0.317. Is this a slow velocity, relatively speaking?
So why
Yeah.
wait?
No. Relatively speaking to our graph, this is the fastest velocity it's ever going to reach.
Yeah, that's farther away from zero.
Because it's farthest away from zero on that axis, right? And that happens right in the middle. Hold on 1 second, okay? So then if I go here, which is my next peak, right? Okay. Where am I on the position graph? Well, yeah, but I mean, where am I relative to the bottom and the top? Pretty much right in the middle, right? And if I go here, a little bit farther, right? This next peak down here, right? I'm pretty much halfway between the top and the bottom there.
So that means
That means I'm right in between the farthest space and the closest.
So right in between, that's where it's
that's like where the
That's
bar
the
is.
fat. Yeah, that's where the bars are. Yeah.
Wait, what?
And that's the fastest I'm ever going to reach. Okay.
Why? How does that work? How does that work? Like,
When I turn the recording off, I'll explain it to you.
Oh.
It has to do with gravity. It's like when you're coming towards the middle, you're going like downward, right? But then when you're coming away from the middle, you're actually going back upward. So gravity's helping you on the way down, but it's slowing you down on the way up.
It's like
Air
gravity's
pressure, like,
pulling.
stop
That
you.
helps it not stop, but slows you down a little bit. So we actually, Julie, if we look here, right? Down here, the fastest point we can reach is negative 0.315, right?
No, like, you keep going back and forth, you're gonna slow down.
Yeah,
Like,
because like here, Julie.
You Hawks run one.
Boo.
Boring.
Can we like do 2 runs?
It's still moving.
You can go. You can like record multiple runs.
so
Is that my fault?
at the bottom.
No, I think like.
So that's like when on
Go
the
ahead, Ellie.
On the bottom of the hill. So
Yep.
That's when it's closer to the.
The bottom of the red hills is closest to the machine.
Yeah.
The top of the red hills is farthest away. The bottom of the blue hills is passing through the middle. So the velocity values. Hold on. Guess if you look at the equation for those values, guess what the equation is like? Yeah, they're sine and cosine functions. So.
We should go.
Wait, how did we? Why
I feel like
did you
we should
say
make this.
All right. That's part. Wait, that's part 1 of your lab. Okay. If you.
Wait, why'd you say it?
Okay. If you look at the lab, there's a part 2 and a part 3. On Friday in class, I'll have you guys do part 2 and part 3 by yourselves. Now that we know what the graphs look like and you can do some analysis, that's what we'll do on Friday. We'll continue on with this lab on Friday. Good job today, everybody. It really is kind of a difficult concept. You guys seem to be getting it, so go from there. Okay? Hold on 1 second.
He's done.